Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to give you some advice here on how to do number 123 here in chapter 12 in your textbook here. So what we've got is we've got this object as represented by this sphere here that's moving along this curve defined by y equals 0.5x squared. And here are some conditions here. It says in the problem that t equals 0, x would be 0, and x dot would equal the speed, which is equal to 1 meter per second. Now the reason x dot and the speed would be equal is because right here the path is horizontal. That's not true anywhere else along the path, but right at that instant the speed would be x dot 1 meter per second. We're also given in the problem here that the acceleration is 0.1 meter per second squared, but that's just the tangential component. So that's the rate at which the speed is increasing. What we're looking for here is the velocity and acceleration 5 seconds later. So first thing I already did here is I defined a position vector here that I drew in blue, r, and that position vector would equal x I plus yj. Now whether this is going to get this done or not, I'm not sure. I think it's a good place to start. From the position vector, we can derive a velocity vector for it from direct differentiation. So that's going to be x dot I plus x dot j. The x dot is coming from this. Here's y. And if you time differentiate this, and keep in mind you have to product or chain rule this, you got to bring down the 2, and that's why that becomes a 1, x to the first power times dx dt. So if I kind of investigate this and think, one of the questions we're looking for is the speed. That's this guy. And this equation here, we don't know the speed, we don't know x dot, and we don't know x. So this equation's got a whole bunch of stuff we don't know. I'm going to go ahead and differentiate it anyway here and then talk about how, other things to do here. The acceleration vector we get by differentiation of this equation here. So that's going to give us x double dot I plus, and then we got to differentiate that term. That's going to give us an x dot squared plus x double dot. And again, that's just coming from product rule, derivative of the first times the second plus derivative second times the first. All right, so there are a whole bunch of things we don't know here either. We don't know the magnitude of the acceleration. We don't know x double dot. We don't know x dot. We don't know x. So this equation has all kinds of unknowns in it. Now, we can use it to write an equation. Here's what we do know. I do know that if we take that acceleration vector and we dot it with a unit vector in the direction of the velocity, we would have to get this 0.1 meter per second squared here. That'll allow us to write one equation, but we're still a long way from solving for anything. This would have to be true. But again, I'm counting like, 1, 2, 3, 4 unknowns in this. So because I'm counting, 4 unknowns, I think at this point right here, I'm going to stop with this analysis and start thinking about something else. All right, now I'm going to focus on this variable here, s, where this is the distance along this path. And this guy right here, let's start with this. We know something about the acceleration here, the tangential acceleration. So the speed of this particle is equal to ds dt. Now you notice I'm leaving vector symbols off of this. These are going to be written kind of in a scalar formulation. And then the tangential acceleration of this particle is dv dt, which we can write a couple of different ways. One is dv dt, but another way is dv ds dt. Now, I'm going to kind of start with this now. The question is, which form do we want, this one or the second one here? Well, if I look at what we're given time information. We're trying to find, we're given this t equals 5 seconds. So since we're given this, let's focus on this guy. So I'm going to rewrite that dv is equal to the tangential acceleration times dt. Put a little NCU for note consistent units. This is going to integrate to v equals 0.1 t plus a constant. Now the constant we can get because at t equals 0, the v is 1. So 0, 1, the constant must be 1. So v is equal to 0.1 t plus 1. And now 5 seconds later, we can put a value here. Now I'm going to let you folks, this is your homework problem, but you put in a 5 here. Suffice to say, we have the v here. So I'm going to go over here and say, all right, at least kind of list this as a known value. Magnitude of v at this point, again, you're going to work it, is now a known number. Now, as I kind of look back through my previous work, where could we use that? Well, here's this velocity function here. The magnitude would be defined by Pythagorean theorem. So we'd have that number squared equals x squared plus x dot squared. These values, though, x and x dot, still not known. So we do have the magnitude, but we still don't have these guys. So now let's go back here to this type of math and take this a little further. Let's see what we can do with this one now. So that tangential acceleration, 0.1 meter per second squared, we can write it dv ds dt. Now the ds dt is v, so I'm going to go ahead and write that v dv ds. This is separable now, so this is going to read 0.1 ds equals v dv. This is now going to integrate to 0.1 s plus v squared, oops, not plus, equals v squared over 2 plus a constant. Now, when s is equal to 0, the particle is here, and we're given a speed. So that's going to allow you to nail down that constant. Again, I'm going to let you folks do that, but this is now a function that is known. This is now a function that is known. Now, what can we do with it? Since we know the velocity, you can put in a time, which means you can calculate a velocity and put that value there. Then out will come an s. Now this is an arc length. So now the million-dollar question, what do we do with that? All right, well, once you have the arc length, now let's talk about how the arc length is calculated along this path. So arc length is a one-dimensional quantity calculated by looking at a one-dimensional element. That green that I just drew would have a length ds. It can be thought of as a horizontal dx displaced with a dy. So displacement to the right by an amount dx, displacement up by an amount dy. And that's going to give me the green one there, which is a ds. These are related by Pythagorean theorem. ds squared is equal to dx squared plus dy squared. It's real easy to solve that for ds, just square root both sides. Now, as far as setting up for integration, if I want to integrate with respect to x, you factor an x out of this. If you want to integrate with respect to y, you factor a y out. So I'm going to factor an s out of this, and a dx out. Let me state that again. A dx squared out of this. If we factor dx squared and then square root it, that dx we can write outside, and this term becomes 1 plus dy dx squared. So this term represents an infinitely small little ds. The total arc length would then be the integral of this expression. Whoops, let me go back and redo that s there. All right, so the total arc length, that looked like an integral, is going to equal the integral from 0 to some x value, which we don't know, times the square root of 1 plus, dy dx squared. Looking at that function, let's see, dy dx squared, that would be 1x squared. So I guess that's just going to be 1x squared dx. And the unknown is right here. So this thing is looking like some sort of trig function. What I would do is this. Keep in mind that we know, if I backtrack here, from this work right here, we would know the arc length. So keep in mind the left-hand side of this integral is a number. And what you can do now is set up an integral in Excel. Treat it like an area calculation. F of x dx. Set up an integral like you see me do in Excel a lot, where you run like I equals 1, 2, 3, 4, 5. We're going to treat this like an unknown. So put just a value, say maybe b there when you do the delta x part. Remember, when you do Excel, the first thing we typically do is we get delta x is b minus a over n. So in Excel, just put a number here like 5 or something. Minus 0 over n, and probably use something like 20 points. And then have it calculate all the x values, all these function values, then have it calculate your area here, just like you see me do in Excel. And again, maybe what I'll do is make another video on working on this. And then get a number. Now remember, what you're going to do here is you're going to guess at that. put like 5 or something. Work this integral, get a value, compare it to this. If your value is smaller, increase this value. And once you have the Excel sheet done, it'll be real easy. Just change the 5 to a 6 or a 7 or 8 and change it to whatever value you have to, so that this integral equals this calculated number. Once you get this value to make your integral match this number, this value is the x value in the here in this picture. So I think that's enough, at least for this video. Probably what I'll do, I should probably make a separate one on how to handle this, because that in and of itself is not super easy. But hope this video gets you at least moving along on that problem. And back up, once you have x, what do we do with that? Well, now, if we have x and we have the v, when we go back and look at this function now, you can write whatever v squared is equals x dot squared plus x dot the quantity squared, and this will have only one unknown, x dot. Right? Moving down into this equation now, let's see. X dot would be known, x dot known, x also known, x double dot still unknown, and the acceleration. Think about what you're going to do with that. I would say at that point, I believe you'll be able to do this. Let's see, x dot, yeah, this part right here. When you take this acceleration vector, dot it with a unit vector in the velocity direction equals 0.1, you're going to get an equation out of it that you'll be able to solve for x double dot. So not a super simple problem, but I think that should, my outline here should work. So good luck with it. Have a great day.